Hi everybody, in this lesson we are going to be covering the simplex method. And we are going to be, in this course, only working with standard maximization problems. So there are other problems we could do, but we're going to stick to just this one type. Looking back at our prior section, we used the graphing method for solving linear programming problems. But it's limited. That only works for two-dimensional problems, so you can only have two variables, x and y. And it requires solving the system of equations for every corner point that exists. So it worked fine for those situations. However, real life optimization problems could have thousands of variables, so we certainly aren't limited to just two. That could mean thousands of constraints, astronomical numbers of corner points, and making the above technique impossible to carry out. So what do we do if we have to move out of this two-dimensional world? Well, we need a new method. We can't just graph it and find the corner points anymore. So the simplex method is the way to do that. Basically, the simplex method is an iterative process. It's repeated over and over again. You begin at some initial feasible solution. Usually it's at the origin. So notice the 0, 0 was usually one of our corner points. It was one of the options. It never maximized anything. It could minimize it. So usually on this, we're going to start at the origin because that's almost always a corner point. And then each iteration that we do will bring us to another corner point. Without seeing it, that's what's going to happen. And usually it's an improved value of that objective function. So 0, 0 is definitely not going to maximize it. Then we'll arrive at another corner point and it will be better. And then we'll arrive at another corner point and it will be better until we reach the end. So the iteration is terminated when we find that optimal solution. We will only be doing what we call standard maximization problems. Yes, there are other types. But in a standard maximum problem, first of all, the objective function is to be maximized. So we will only be maximizing in this way. The variables involved are non-negative. So that's your x1, x2, x3. In your question, what that will mean basically is it's a lot of times it's a word problem where only positive answers make sense. Like how many, TVs, VCRs, Blu-ray players, and those can't be negative numbers. So that's all that means is that typically the variables are going to be non-negative. And the linear constraints can always be written so that the expression involving the variables is less than or equal to some non-negative constant. Okay, so some example then of a non-standard, something that wouldn't qualify as this? Well, we are maximizing, so that checks number one. We're assuming x1, x2, and x3 would all be positive for some reason in the context. But the reason why this one would not fall is because this right here should be less than or equal to. So your constraints all have to be less than or equal to. And if you think about it, that makes sense because if we're going to be maximizing it, we have this something that can be, we wouldn't want to be out in an unbounded situation. We'd want to be in this bounded area and we'd be finding the maximum. Because if we were unbounded, there probably isn't a maximum. So all this is meaning number two, that all those variables are non-negative. So in a standard maximization like number two, this is what we're going to be doing. We're going to be maximizing all of our constraints are going to be less than or equal to some non-negative value and all of our variables positive. Okay, so these are the types that we're going to be doing. You don't really have to worry about that. They're just the only types you're going to be getting. Okay, so let's go ahead and think about this problem from example 2 is going to be our first example. The first thing you do in a simplex method is that you convert the constraint inequalities into a system of linear equations by the use of what we call slack variables. Okay, so these are the two constraints. They start off as less than or equal to inequalities, so we're going to turn those into equations. The idea is that, think over here, think back to something simple. If you have a less than or equal to statement, so 3 is less than or equal to 8, that means that this is possible. It means I'm able to add something to 3 to get exactly 8. If you have a less than situation, you can always add something to that left-hand side to equal the right-hand side. So that's what we're doing. We're saying, well, if these are less than or equal to 10, then if I take these and I add something else to it, I should be able to get exactly 10. Okay, same thing with the next one. If those are less than or equal to 8, then I should be able to add something. You have to use a different variable, so I'll say y2 on this one, something else, to that in order to get 8. So y1 and y2 are called our slack variables. Just as a note, sometimes you don't have x1, x2, x3. Sometimes if your variables, you'll see these in some examples, like if you're using x, y, and z, that's used also a lot, then a lot of times with that, your slack variables end up being u, v, and w. It just depends on the video you're watching or the text that you're using. So usually if you're using the x's with the subscripts, then you use y's with subscripts for slacks. If you use x, y, and z for your regular variables, then u, v, and w end up being your slacks.